Hi everyone, this is worksheet 13.1, SP2 hybridization. In this worksheet, we're going to see how the SP2 hybridization works as a combination of 2s and 2p orbitals, and where we get the 120-degree angle that we know so well from the SP2 hybridization. So let's start by pointing out that the atomic orbitals are going to have 1 2s and 3 2p spots for the electrons to occupy. And let's say that we have 3 electrons, like in the case of the molecule BH3. So that means there's going to be 2 down in the 2s and then 1 up in the 2p, like that. At least that's what you might think at first glance. However, in the case of BH3, that will not happen. Instead, you will get 3 degenerate sp2 orbitals, and then you're going to have a 2p that is perpendicular to those. And so the 3 electrons are going to spread out according to Hund's rules and occupy those sp2 orbitals like that. Okay, so we're going to see where that 120-degree angle comes from, and we're going to have 3 separate hybrid orbitals. Each one of these is a different sp2 orbital, and each of those is going to be facing a different direction, 120 degrees from each other, and we're going to assume that they are composed of a 2s and then also a 2p orbital going in the z direction and a 2p orbital going in the x direction. We're going to assume that it's lying on the xz plane, so there's going to be no 2py orbital characteristics in any of our hybrid orbitals, because that's going to be this orbital up here. That's the 2p orbital sitting out away from those, up perpendicular to the plane of our hybrid orbitals. Okay, there's going to be some normalization constants out in front of each of these. We can call it A1, B1, and C1, and those just represent the different proportions of each of the atomic orbitals within the hybrid orbitals. So that means there's going to be a different coefficient for psi2, and then also psi3. I'm only going to focus on these two for this particular video, though if you wanted to, you could try to calculate the coefficients for this third one, but I'm just going to get the coefficients for the first two right there. Okay, so let's define our atomic orbitals here. We're going to assume that the 2s orbital can be just described by the following function: 1 over 4 pi to the 1/2, and then some radial function of r. Then down here we're going to have 3 over 4 pi to the 1/2, 3 over 4 pi to the 1/2, and then these functions here. Like so. And that's what we're going to use for our s and p orbitals. Next, we're going to assume that all of these orbitals are going to have equal proportions s atomic orbital. So we can say that A1 equals A2 equals A3. That's just saying that they all have equal amounts of s orbital to each other. And in addition to that, we're going to say that a single s orbital is going to be spread out among those 3 sp2 orbitals, And that should make sense because over here we only have one 2s orbital. And so the way that we're going to spread that 2s orbital around to each of those evenly is to insist that a1 squared plus a2 squared plus a3 squared equals 1. All right? But since each of those just equal each other, this is equivalent to writing 3a1 squared equals 1. So then when we algebraically rearrange this, we get a1 is equal to 1 over the square root of 3. So that means that psi 1 is just going to equal 1 over square root of 3 times the 2s orbital plus b1 times the 2pz orbital. And then we're going to assume that c1 equals 0 because we're going to align this first hybrid orbital along the z-axis. So if we have depicted here the pz orbital looks like this, if this is the z-axis here and this is the x-axis here, then we're going to make our hybrid orbital, which I'm going to use a different color for. Our hybrid orbital is going to look something like that. At least our first one will. And then we'll see a little bit later that our other hybrid orbital is going to kind of come out in this direction like that. So it's going to be partially x and partially z together. But we're just going to focus on this green one for now, psi 1. Okay, and the first step is going to be to insist that we normalize this hybrid orbital. And so I'm integrating over tau, which is going to represent the radius and the angles and just all of space. And we're going to insist that because the hybrid orbital needs to be normalized, that this integral is going to equal 1. And so then I'm going to need to take this and FOIL method it. So I'll get 1 over square root of 3 2s plus b1 2pz, and then square this, integrating over d tau. So then I'm going to FOIL this. So I'll get this times itself, and then this times this, and then this times this, and then this times itself. So then once I do FOIL, I'm going to get 1 over the square root of 3 times the 2s orbital times 1 over square root of 3 times the 2s orbital plus 1 over square root of 3 times b1, 2s times the 2pz orbital. I need to write down my integrals here. This is integrated over tau, this is integrated over tau, plus b1 times the 2pz orbital times 1 over square root of 3 2s orbital, integrated over tau, plus the integral b1 times 2pz times b1 2pz d tau. Okay, so the next step is to realize that in this orbital, or sorry, in this integral right here, I'm integrating over all of space of these two orbitals times each other. But remember, these are orthogonal. So that means this integral is just going to equal 0. And the same is going to be true of this one right here. That one's just going to equal 0. Now the next step is to recognize that I've got these two orbitals times each other, the 2s ones, integrated over all of space. That's just going to equal 1. So I'm going to get 1 over square root of 3 times 1 over square root of 3. And that's going to be 1/3, because the 2s orbitals integrated, multiplied times each other, integrated all over space equals 1, and I can pull these out of the integral, and so that just becomes 1/3. A very similar thing can be done over here with this one. I've got the two orbitals times each other, integrated over all space. That's just going to equal 1. I can pull these b1s out, so I can say that this is just plus b1 squared, like so. And this whole thing just equals 1, according to that normalization condition. Subtract 1/3 from both sides. I get b1 squared equals 2/3, or by extension, b1 is equal to the square root of 2/3. So this means that in the end, we get psi 1 is equal to 1 over square root of 3, 2s, plus the square root of 2 over 3, 2pz. and that's our first hybrid orbital. Okay, now I'm starting over with a new page here, and we get CHE2, and we already know that A2 is 1 over square root of 3, and that's the 2s character, plus B2 times 2pz plus C2 times 2px. And we can't just cancel out C2 this time because we're assuming that this hybrid orbital does not lie along the z-axis. So it's somewhere on the xz plane, but it's not exactly on that axis. So the first step is that we're going to require that the integral of psi1 and psi2 integrated over all space is orthogonal. So those need to equal 0. And once you do that, then you're going to do something similar to the FOIL method, where you're going to get A1 2s plus B1 2pz multiplied times A2 2s plus B2 2pz plus C2 2px. And you're going to do sort of a 6-way FOIL, kind of like this. And then once you do that, and then integrate over all space, you'll see that only this one times this one will not equal 0, and also this one times this one will not equal 0. And once you perform all those integrals, then we can say 0 equals 1/3 plus B2 times the square root of 2/3. And then if we algebraically rearrange this, we find that B2 just equals negative 1 over the square root of 6. And there we found B2 by taking advantage of the orthogonal nature of psi1 and psi2. Okay, the final step before we get the last coefficient is to insist that this hybrid orbital be normalized. So we get that. We're going to take this function here, multiply it times itself, so we're going to get a 3×3 FOIL. But again, only the terms that have an orbital times itself is going to equal anything other than 0. And so then once we do that trick, then we're going to get 1/3 plus 1/6 plus C2 squared equals 1. And then when you manipulate that algebraically, you get C2 equals 1 over square root of 2, like that. So therefore, our psi2 equals 1 over square root of 3, 2s, minus 1 over square root of 6, 2pz, plus 1 over square root of 2, 2px. All right, we're almost done here. Now we need to find which direction this orbital is pointing. Like, what is the angle compared to the first orbital that we had? Because, like we said, that first orbital is going to be aligned along the z-axis, and then our second orbital is going to be somewhere out in this direction. And we want to know, what is this angle right here between the first orbital, which is aligned to the z-axis, and the second orbital, which is aligned to the x-axis, like so. Okay, so in order to do that, we're going to need to find the location of the hybrid orbital's greatest amplitude. Now, right before I do that, I'm going to write out the definitions of the 2s, 2pz, and 2px orbitals that I had on the last page. This is just going to be some function of r, 4 pi, and this is all to the 1/2 power, like that. 1 over the square root of 3. And remember, the s orbital was entirely just made of r. And then this one is going to be the square root of 3 over the square root of 6 cosine theta, according to our definitions of the s and p orbitals. Square root of 3 over square root of 2 sine theta. And the cosine phi just goes away because we're assuming that phi equals 0 because we're stuck on the xz plane. So phi just equals 0. All right, so we're going to get the derivative of psi 2 with respect to theta because that's going to allow us to find the local maximum in terms of our amplitude, and set this equal to 0, because when you set the derivative equal to 0, you find that local extrema, like the minimum or the maximum. And this is going to equal RR 4 pi to the 1/2 square root of 3 over square root of 6 sine theta plus square root of 3 over square root of 2 cosine theta. And I can just divide both sides by this term right here, so that just goes away to 0, and I'm left with just this sine and cosine equaling 0. So let me rewrite exactly what I get there. I'm going to have square root of 3 square root of 6 sine theta plus square root of 3 over square root of 2 cosine theta equals 0. And now I'm going to divide everything by cos theta, even this one, though of course that's just going to become 0. And then I'm also going to multiply everything times the square root of 6 over the square root of 3. Square root of 6 over square root of 3. Those are going to cancel out. Square root of 6 over square root of 3. Of course, that doesn't matter. That just goes to 0. And so then once we're done simplifying all that, we get the tangent of theta, because that's what this expression means, plus the square root of 6 over the square root of 2 just equals 0. And I can subtract this from both sides. And I get that the tangent of theta is equal to the negative square root of 6 over the square root of 2. But that's just the negative square root of 3. And if you then take the arctan of both sides, then you get arctan negative square root of 3, and that's going to be 120 degrees. And there you have it. That is the angle of our other hybrid orbital. And if you wanted to, you could work it out with the third orbital, but I'm going to leave that as an exercise for you. That's it. Thanks.